Okay, are there any questions from what we discussed yesterday? Is my voice audible at the back? Okay. So, any of you have any question? Yes.
Last day that is it that you need a special type of for mathematical series because regular black particular bursts and as a time dependent yes and so my question was that EPK has a lot time only mass time to take a time is like this
Yeah, we can certainly try to do that. It's just a more difficult problem, right? So, the idea is that I try to solve the easy problem first, easiest problem, and then we can try to go beyond and try to address the more difficult problems. Yeah, it's in principle doable. Nobody has done it, but in principle it is doable. Because it's difficult, clearly, right? And I mean, it's a challenging problem for you to do it. I mean, yeah, so people have done whatever best they can do, right? And those are for the supersymmetric black holes. So, counting microstates is not easy. And mainly the idea is that, as you saw, that for supersymmetric black holes, you have these two different limits. Okay? In one limit, it's just described by a black hole. In the other limit, it's described by a set of constituents, right, which have weakly interacting quantum interaction. And the supersymmetry allows us to connect the results from one side to the other side. Okay? That technique doesn't exist for these other black holes in the absence of supersymmetry. So, there you really have to know how to do the counting directly when you have a black hole configuration. Okay? That's why it's more difficult. Yes.
what was it then is a problem when the particle torpedo were faster at that part
No, that's in fact when you count. Because when the particles are delocalized beyond the event horizon, that means the gravity is weak, right? You can ignore the effect of gravity and just think of this as a collection of normal quantum particles, and there you can do the counting, right? When the particles are all inside the horizon, you don't see them directly, right? We only see the gravitational effect, and that's where we don't know how to do the counting. Okay, so let me just quickly remind you what we had seen last time. Okay. So, we are dealing with supersymmetric black holes. Okay. And for supersymmetric black holes, we took the simplest system. Okay, a black hole carrying some charge, extremal black hole. Okay. And there we said that we can write the total charge carried by the black hole as some integer n times the q naught, where q naught is the minimum unit of charge. N is an integer, we keep fixed. This one can be varied, okay, by as you move in the moduli space of the theory, right? Weak coupling, strong coupling, this is like changing the moduli is like changing the fine structure constant, right? And a unit charge that the electron carries can be changed by changing the fine structure constant, right? That's why q naught can be varied. And then we consider two limits, one where n q naught is large. In this limit, we saw that the Schwarzschild radius is larger than the radius that quantum mechanics allows us to have, right? Quantum mechanics tells you that you cannot localize a particle beyond a certain minimum value, which is 1 over m. Okay. And in this limit, n q naught large, okay, the Schwarzschild radius is big, so the black hole description is good, right? The particles are all localized inside the horizon. So, black hole description is good. And you calculate the entropy by this formula A over 4G. The other limit is n q naught small. In this limit, the 1 over m, which is the typical length scale of a quantum particle, okay, beyond which you cannot localize it, that becomes larger than the Schwarzschild radius. So, where n q naught is small, the system can be regarded as a weakly interacting system of n particles, each of charge q naught. So, here it is just like a normal quantum system. So, we quantize and count states. Number of states, which will denote the omega, and then you compare S and log omega. The reason that you can do it is because of supersymmetry. So, let me write that also. So, in the moduli space, okay, as we discussed, the moduli space corresponds to flat directions in the potential, and I am just drawing one flat direction. Okay. So, along this q naught varies. Okay, as you move in the flat directions, the minimal unit of charge that the black hole can carry varies, and we will see an example later. So, we can look at two different points in the moduli space. Here, the quantum description is good. Here, the black hole description is good. And then supersymmetry tells us that omega does not change along the moduli space. So, even though we are counting states here, and we are calculating the black hole entropy here, the result does not change along this line, and hence it makes sense to compare the S that we calculate using A over 4G. Maybe I should write there A over 4G. Why? Okay, I think maybe that is a problem. No, it's, we'll see that this becomes essentially a collection of harmonic oscillators. Okay, so it's really easy to quantize this system, and the final formula that we deal with really is just a product of harmonic oscillators, right? But we'll see this in more detail later. Okay, so right now the main important point is it is possible to count states because it's a weakly interacting quantum system. Okay, is this okay? Are there questions? And this is where we arrived last yesterday. No potential, yeah. So this is V versus this is V. Moduli by definition are scalar fields which have no potential, right? So you just vary the scalar field, right? And here the yeah, quantum effects are important, right? Gravity is not important. Here, gravity is important and quantum effects are not important. Now, there are two subtleties in what I have said so far, and let me mention those first, okay, and then we'll actually work out an example of a counting. Okay, what do you mean by weakly interacting quantum system? Hopefully it will become clear. So the certainty number 1 is that what we considered a Einstein-Maxwell theory, where we have gravity and one vector field, right? One field like a Maxwell field, and that is really what we have in nature, right? We have only one electromagnetic field. But as we discussed, string theory has many vacua, and we are looking at a particular class which are a supersymmetric vacua, and most of these vacua have more than one vector field. Basically, it means that a particle can carry not just one charge but several kinds of charge. Okay, for every vector field, we will have a associated corresponding associated charge. So, a generic theory, string compactification, with n greater than or equal to 2 supersymmetry has okay, this is also called the U1 fields. If this is not familiar, you don't need to worry. It's like as if instead of having one Maxwell field, you have multiple Maxwell fields. So this means that state carries multiple charges. So we have Q1, Q2, and we can write Q1 is equal to N1 Q1 naught. I write it the other way. So let me say up to QK in the K fields like this. Well, these are the unit charges, right? The minimum charge that the state can have, Q1 naught, Q2 naught up to QK naught, and you have N1. These are integers. Okay, you can have state carry integer multiples of these charges, but the principle remains the same. We at one corner in a moduli space, these units are small, so that these combinations are also small, and we can think of this as a quantum system, okay, weakly interacting quantum system. And at the other end of the moduli space, these are large. The ends are fixed, but these units become large, so that we can think of this as black hole stage. Is this clear? So this is a small faculty that you typically have to deal with, a state that carries different kinds of charges, okay, not just one charge. But we can carry out the analysis exactly as we described before. We can write down the expression for the entropy as a function of the charges, and calculate the area as a function of the charges and calculate entropy by the same formula. On this side, you now have N1 constituents of one kind, N2 constituents of another kind, N3 constituents of another kind, and so on. So this is still a weakly interacting quantum system, but of multiple kinds of objects, right? Instead of having all of similar objects, you have multiple different varieties of objects. They are all interacting with each other, and you have to quantize them and find the number of states. Yes.
So does the debatable charges formal superselections at both are evenly superbody?
You can superpose, but here you are talking about if this the number of states carrying a fixed amount of charges, right? So the state that you are considering, right, are fixed charges. So one kind of charge cannot get converted to another kind of charge. Okay, so you have different a given state will carry fixed amount of charge of each kind. Is this clear? Okay, the second subtlety is more subtle. Okay, so let me, which is the, what is that? 0 is the unit. So this means that this is the minimum charge of type 1. Right? See, there are different kinds of charges, right? First kind of charge may have a minimum value. Imagine that in our world, right, instead of having one kind of charge, you have two kinds of charge. Okay, two different symmetries of two kinds of charge, and then the first kind of charge may have a unit, right? That is what I am calling Q1 naught. Second kind of charge may have a different unit, right? That I am calling Q2 naught, and so on. They are not they are different kinds of electromagnetics, right? There are multiple electromagnetic fields, right? Instead of having one mu, one vector potential, you have A1 mu, A2 mu, up to AK mu, right? Maybe I should have written this. So multiple U1 gauge fields. So we have A1 mu, A2 mu, up to AK mu. Okay, these are different vector potential. Each of them have their source, right, which are the corresponding charges. And those sources, the minimum unit, I am calling Q1 naught, Q2 naught, up to Qk naught. Is this clear? Right? Just imagine that in our world we have two kinds of charge. Right? Then you have to specify, the electron has to be specified not by one E, but a E and E prime. Right? What amount of charge of first kind it carries and what amount of charge of the second kind it carries. Okay? If you are familiar with nuclei, right? To specify a nucleus, you have to specify the number of protons and number of neutrons. Right? So that means they need to specify two data, right? Those are not gauge charges. They don't couple to gauge fields, but it's similar to this. That you have to specify both the number of protons and number of neutrons to specify a nucleus. So those are like N1 and N2. Yeah, so I didn't include magnetic charge just to avoid confusion, but each particle can carry both electric and magnetic charge. Right? So the actual number of charges that it can carry is double of what I have written. Okay, that's also certainly possible. Okay. So when we count states, we'll fix the charge. Okay, if you want magnetic charge, you can add those as well, but we keep the total charge fixed. Take the constituents, right, which carry the minimal charge, look at their quantum mechanics, and then see how many states we have. Is clear? Okay, so the second subtlety is that I told you something which is not quite correct, right? I said that we count the number of states here, right? And then as you vary the moduli, the number of states don't change, right? But what the actual statement is not quite this. The actual statement is that number of bosonic states minus number of harmonic states don't change. This combination do not change. Okay, these are all supersymmetric states. Yes. The difference doesn't change. No, so multiple charges, same particle. Same particle carries multiple charge, right? N1 of first kind, N2 of second kind, up to Nk of some kth kind. Right? So you fix the state, right, carrying multiple charges. Then we are asking how many quantum states are there with that property. Right? That's what is our omega is. Right? How many quantum states are there with that property? Right? So that's the counting omega. Right? And what I am saying now is that what remains unchanged is not that, but you have to count separately how many bosonic states of that kind are there and how many fermionic states of that kind are there. Right? Which means how many integer spin states and how many half integer spin states. Right? Calculate the difference. Right? That difference is what remains unchanged as you go from here to here. Is that clear? Right? Not the number itself. If it's not clear, just ask. Clear? Okay. Okay. But this is a problem, right? Why is this a problem? On this side, when you are doing quantum description, here of course it's not a problem. You can count separately because you are doing quantum mechanics, right? You can count separately how many bosonic states are there, how many fermionic states are there, and calculate the difference. That continues to here. So this means that here we can calculate the number of quantum, the number of bosonic states minus number of fermionic states. But entropy is not that. Entropy is not log of that, right? Entropy is the log of number of bosonic states plus number of fermionic states. So it just counts everything. So then the question is, if we know this object, right, from the gravitational side, and if omega here is the difference between the number of bosonic states and number of fermionic states, how is it possible to compare the two? Is this clear? Right? So that seems like a puzzle, right? You cannot do it. Is this problem clear? I'm quite convinced that everybody agrees that it's clear. Okay, no. Okay, so I'm saying that omega, right, which is protected, which you can calculate here, you can calculate everything here. This is quantum, just normal quantum mechanics, right? Bosonic states, fermionic states, you can individually calculate. But what is unchanged is the difference between the bosonic states minus fermionic states, right? So omega, this omega, which you can calculate from the at this point, is the difference between the number of bosonic states minus number of fermionic states. We are trying to compare that with this. This is what you can calculate from gravity, right? From the gravitational side, we don't know separately what is bosonic, what is fermionic, right? We only know the total degeneracy. So then the question is, this is calculating the difference between number of bosons and number of fermions, and this is calculating the log of the sum. Then how can we compare this? It turns out that here again supersymmetry comes to rescue. So supersymmetry, basically this I'll elaborate later, but let me just say how this problem is resolved. So supersymmetry essentially implies that black holes carry zero angular momentum. So if a state carries zero angular momentum, what can we say about the state? It's bosonic, right? So this means that all microstates are bosonic when we have black holes. Supersymmetric black holes. Okay. So in other words, here when you do the calculation, right, we may find bosons and fermions because here it's not a black hole, right? Here the description is that it's a normal quantum system. You're quantizing a bunch of particles, right? Some of them may be bosonic, some of them may be fermionic, and you are looking for the ground states. So here you can have both bosonic states and fermionic states. But by the time you have gone here, right, we only have bosonic states. we have supersymmetry everywhere. But supersymmetry by itself is not enough to say that the angular momentum is 0. It's supersymmetry plus the horizon of the black hole, right, which together implies that the angular momentum is 0. No, that is okay. So the point is there is a multiplet structure, right? That multiplet structure you have to factor out. So when you are saying that the state is bosonic or fermionic, right? We are asking that after you have factored out the super multiplet structure, right? Then how many bosons and how many fermions are left? Okay. So it's like imagine a super multiplet, right? Goes from -3 up, spin -3 up to -3 half. Okay. Then a bosonic state, a zero angular momentum state will go from -3 up to 3 half. Angular momentum half state, right, will start from -1 and go up to 2, right? They'll be shifted. So what we are counting is the central value of the central value of J3 of the multiplet, right? That's what I mean by this angular momentum. Okay, there is a technical reason to why this separation happens, because there are some zero modes living outside the horizon, right? So the horizon doesn't know anything about those, but the relevant counting that you have to do, right, which is that after factoring out this multiplet, is exactly that all have zero angular momentum. Yes.
We have all difference because he entered half of the career period up at speed you can do separate.
Yeah, but here what happens is you have not zero angular momentum only on the J3 direction, it forces spherical symmetry because of a symmetry, right? And then there is a further argument that all states have the same angular momentum because it's in the the near horizon geometry forces you to be in the microcanonical ensemble where you fix the charge once and for all. So if all states have the same angular momentum, and if the average is 0, then each state must carry zero angular momentum. No, only supersymmetric extremal black holes. There are only 40s. Yeah, what we discussed yesterday, for example, right, were supersymmetric extremal black holes, right? Those are the only ones that we are considering now, right? Because as I said, those are the only ones for which we have this property that we can go from weak coupling to strong coupling, right, without changing the number of states, right? Or more specifically, without changing the difference between the number of bosonic and number of fermionic states. Yeah, I'll elaborate it maybe when we discuss the near horizon geometry in some more detail. Right? Basically, as a consequence of supersymmetry algebra, you find that it forces you to have perfect spherical symmetry. Right? And perfect spherical symmetry means it's rotational invariant, right? And that's the statement that you have zero angular momentum. Right? But I'll try to elaborate on, I mean, we cannot probably do it without understanding the near horizon geometry in more detail. Right? But that's basically the argument. Yes. Yeah, they are both in them. So you have to factor out the super multiplet. Right? So as this is what I was saying. Then imagine that you have a super multiplet which goes from -3 half or say -2 to 2. So you go from -2, -3 half, all the way to 2. Okay. So this has equal number of bosons and formulas. Right. This is not what we are discussing here. A generic state, what it will have is that you will have this, okay, and then it will be multiplied by some J3 equal to M state. Right. Once you multiply it by this J3 equal to M state, this will get shifted to M minus 2, M minus 3 half up to 2 plus M. Right. So when I said that the black hole are forced to carry zero angular momentum, right? It's forced to carry M equal to 0. Right. This is always there, super multiplet. And the reason that this is not so, that this spherical symmetry doesn't prevent this is because this structure comes from dynamics outside the horizon. Okay. The black hole horizon doesn't know anything about the dynamics that produces this structure. Right? The black holes are also in supermultiplet, right? But they're in supermultiplet because of some dynamics that's happening outside the horizon. Right? The horizon is perfectly spherical symmetric, and that's what forces you to have m equal to 0. Exactly. Yeah. Yeah. Because there is outside dynamics which fixes the supermultiplet, right? Which has to be, which is common to all states, right? Because after all, it's a supersymmetric theory, right? So everything has to form a supermultiplet. But it's m that we are using to determine, say, whether it's bosonic or fermionic, because this is what refers to the horizon. Yes.
So the picture is rather a rural space. Does it called like stream of minute of the horizon or some black hole?
Yes. So this is all for supersymmetric extremal black holes. Exactly. Yeah. Otherwise, there is no reason why. Okay, this flat direction, of course, is true, right? Flat direction doesn't depend on what other considered black holes or anything, right? This is a property of a theory. But the fact that this difference between bosons, number of bosons and number of fermions doesn't change, that is only for extremal supersymmetric black holes.
And that's why you only have horizon. That's what you're.
Exactly. Is this okay? So this is then the principle, right? That we'll use weak coupling. Okay, that's set up a weak coupling theory to calculate the difference between the number of bosons and fermions here, and then compare that with compare the log of that with A over 4 that we calculate here, and see if the results at E or not. Okay, that is a test of whether you can explain black hole entropy from microstate counting. Okay, in this limited context. So now I am going to describe a toy example of what we mean by counting. This will be an example taken from string theory, but unfortunately, this is a simple, somewhat simple system, so it doesn't give a regular black hole. Okay, nevertheless, it will illustrate how we go about doing the counting. So we have seen compactification, right? So we start with a string theory. In D equal to 10, which can be 2A or 2B, okay, or heterotic, but I am not mentioning heterotic because that's a little more complicated, right? Just say 2A or 2B. And then compactify 6 directions, 6 directions on product of 6 circles, or also called a torus. So we take xm to be periodically identified with radius rm, okay, with xm to equal to xm plus 2 pi rm for m equal to 4, 5, 6, 7, 8, 9. Okay, so these are the compact directions. This notation is familiar, right? What this is saying? This is saying basically that this xm direction is a circle. You go to pi r and you come back to the original point. That's what happened on a circle, right? As you travel to pi rm, you come back to the original circle, original point. So this is the meaning of compactification. Pardon? Okay. And the other directions, x mu from mu equal to 0, 1, 2, 3. These are the usual non-compact. Three plus one dimensional space-time coordinates. Okay, and x naught I'll also label as t. Okay, remember I have said c equal to 1, right? Otherwise I would have written c times t. So x naught I have taken and say equal to t. So in this picture, Rm are the moduli. Okay, Rm So each radius of the scalar field, right? Each radius, okay, appears as a field in from the 3+1 dimensional viewpoint. Is this familiar? You have seen compactification. Radius of note that the field wraps around it. Okay, let me write it. So the radius of the say 90 direction, right, will be given by square root of G99 dx9. This clear? G99 is the metric component, right? Metric is what measures the distance, right? So if we have a small distance for small dx9, that distance is square root of G99 dx9. Right? So imagine that x9 we have periodically identified with period 2 pi. Okay? So suppose you have written it as 0 to 2 pi. Then this becomes 2 pi times square root of G99 if G99 is independent of the x9 direction, right? Imagine G99 only depends on the space-time coordinates. So then you see that G99 actually appears as a scalar field, right? The metric was a field, right? So 99 component of the metric is also a field, but from the 3+1 dimensional viewpoint, it doesn't carry any vector index, right? Mu index is not there, so it behaves as if it's a scalar field. But its vacuum expansion value is what controls the period of the ninth circle. Right? This is the length of the ninth circle. Right? So it is in this sense that the radius of compactification becomes the becomes scalar field moduli. Right? So changing scalar field means you can change changing some scalar field, you can change the radius of compactification of the ninth direction, and that scalar field is the 99 component G99. Is this point clear? Right? That metric components knows about the size of the extra dimensions, right? And metric components are fields, right? And in this case, the G99 is a scalar field because it has no vector index, no index mu. So this is the sense. So 2 pi R9 you can think of as this. And then, so this is the sense. This is in which R9 is a modulus, and then you can actually make a coordinate transformation, right, to bring x9 to have period 2 pi Rn and G99 to be 1, right? That's just a simple scaling of coordinates. Okay, whether you think of the metric as being 1 and the x9 period as being 2 pi R9, or you think of the x9 period as being fixed 2 pi and G99 being containing information of R9, they are equivalent. Is clear? So these radii are the moduli. Okay, so we are going to change them to make life simple for us. So in this theory, we consider the following state. Take a fundamental string and wind it once along the ninth direction. Okay. What does it mean? Okay. What it means is that let's do the x9 direction. Do the x9 direction. Okay. So it's a closed string. Okay. you start from x9 equal to 0 and you go up to x9 equal to 2 pi r9. Okay, so the string goes like this. Now, a closed string is supposed to have two of its ends at the same point, right? But 0 and 2 pi r9 are the same points. You have just gone once around the circle. Right? This is the meaning of winding the string around the circle. Is clear? So, we take this string and we consider oscillations. Okay. So, what will be the dynamics of this string? Right? So, take R9 to be large or large R9. Okay, we just pull the string and it starts vibrating. Right? That's the kind of oscillations we are talking about. Right? These are the low energy, low lying dynamics. Those will be the low lying states of the string. Right? A big long string, right? And some waves propagating along the string. You have done just classical strings tied at two ends, right? Here it's instead of having tied at two ends, you have a periodic boundary condition, right? That's the only difference. Otherwise, it's like a classical string which is oscillating. Okay. And there will be 8 transverse directions, right? It's a 10-dimensional theory, right? One of them is of course time, right? So it's a string in 9 dimensions. So there are 8 directions in which cannot oscillate, right? Because there are 8 directions transverse to this. So the degrees of freedom can be written as xi as a function of sigma. Let me write it as a function of x9 and t. Okay, because this is the x9 direction, right? So the string is vibrating, so you have to specify what the transverse position is at x9. Right, that's one. The difference will be a function of x9 and t, right? At different positions of the string, the transverse position may be different, right? Because the string is oscillating like this. So one can write down an action for this. Okay, I'll write it down. You can derive it from first principle. So the action that governs the dynamics of xi is essentially proportional to integral dt dx9 sum over I equal to 1 to 8 where del x9 this is basically the derivative with respect to the x9 direction. Okay, this is the kind of equation that one has for normal strings as well, right? With some velocity of sound appearing in this formula. Yes. Because 9 direction is along the string, right? So the string doesn't move in that direction, right? There's a longitudinal oscillation, right? So it only in the transverse direction, right? That's why it's from 1 to 8, right? Yeah, longitudinal oscillation would have been in this direction. Yeah, but the relativistic string, the motion of the string is, it will be like if you have a string and it rotates like this, but there is a symmetry that tells us that the string which is like this, and if we just shift it, it's not changing the configuration. Right? That's why the longitudinal oscillations are not physical oscillations. in fundamental string theory, right? You may, I don't know whether it has been discussed in the string theory course, but that's one of the properties of the fundamental string, that the longitudinal oscillations are not physical. Yes, only transverse oscillations are physical. Okay, but if you have a normal rigid string, right, there you can also set up longitudinal oscillation in principle. Any other question? So this one actually you can recognize as a 1 plus 1 dimensional field theory of 8 scalar fields. What are the 1 plus 1 dimensions? Time and x9, right? Because that's the direction in the string is, and the 8 scalar fields are the xi's, right? The transverse positions. So you can easily find its quantum states, right? And as you know, in free field theory, quantization of a free field theory basically leads to a collection of harmonic oscillators. Okay, so let me just quickly give the mode expansion. N is integer. Okay, this is this is one difference from normal quantum field theory, where they will do an integral over k. Okay. Here, because x9 direction is compact, this expansion will have to have the property that it should be periodic as x9 changes by 2 pi r9. Right? So that's how you have written in this form. So you can now substitute this expansion in the action, and then the action becomes and xi minus n is actually xi n star. Okay, that follows from this, because this is real, right? Xi x90 is real clearly, right? So if you complex conjugate, this becomes complex conjugated xi n star, and this changes sign, right? So if xi n star is xi minus n, then complex conjugate is the same as the original, right? That's why you have this. So this is what people call, what we normally call complex harmonic oscillator, right? So compare with harmonic oscillator. Which is the action is proportional to half right. So this is, by comparing this, we see that this is like a complex harmonic oscillator with omega equal to n over Rn, R9. So there are in fact infinite number of harmonic oscillators, because the sum over n runs over infinite number of values, and then I also runs, sorry, I should have written the sum over I also here. I also runs from 1 to 8. Okay, there are infinite number of harmonic oscillators, and but we know how to construct the spectrum, right? So the spectrum, the states are basically product over I equal to 1 to 8, product over n, a I n dagger, These are the creation operators. Okay, defined harmonic oscillators of course have commute, and AJN prime dagger is given by this, okay, and the states are constructed this way. Okay, so simple quantization, just harmonic oscillator, right? Except that there are infinite number of them. This is clear, right? And the energy that it has, so energy is, there is a constant part, right, which will not worry about too much, and then sum I, sum over n over mod n over R9, I think that's it, right? Sorry, mod n over R9 times this number RIN. Okay, I should have said what RINs are. RINs are arbitrary integers. So the idea is that any oscillator you can apply any number of times, right? You start with the ground state, right, and apply the oscillator EIN dagger arbitrary number of times, and that's what I'm calling RIN. Right? And every time you apply this operator, you raise the energy by this amount, mod n over R9, because that's the omega. So total energy then is given by this. Is this clear? Okay, but what is really of interest to us is not energy but charge. So you see, if you look at this action over here, this has a symmetry under translation of the x9 coordinate. The energy is the conserved charge associated with the translation of the time coordinate. Right? But this also has a symmetry under translation of the x9 coordinate. X9 is the space coordinate. Right? So there is a spatial translation invariance. You change x9 to x9 plus a, nothing changes. So there should be a conserved Noether charge. You are familiar with the conservation laws, right? Every symmetry has a conservation law. So what is the conservation law for this? Momentum, right? Translation for space-time translation, the conserved charge is a momentum, right? So for shift along x9, right, that symmetry, there is a conserved charge which is the momentum along the x9 direction. So these states then should be characterized also by the momentum that they carry. Right? How much momentum that they carry in the x9 direction. Is that clear? Go back and write here. So each AIN dagger carries x9 momentum n over R9. It is in fact clear from the way this expansion, right? Because we normally write it to the I k dot x, right? K is the momentum. Here I have written n over R9 times x9, right? So n over R9 is the momentum. So it carries momentum n over R9. But unlike in normal quantum field theory, where you have a continuous momentum, right? Here the momentum is in units of 1 over R9. Why is that the case? Yeah, so basically once you have a compact circle, right, once you have a periodic boundary condition, the momentum gets quantized. You have done particle in a box, right? Particle in a box has momentum quantized in units of 1 over L, right? It's basically that is the physics. So that's the reason why you see that the momentum being quantized in units of 1 over R9. And then this, so the momentum for this state, let me write it as momentum is given by sum I, sum over n over R9 times RIN. Okay, because the nth, this particular harmonic AI in dagger carries a momentum n over R9. You are applying it RIN times, right? So it will be n over R9 times RIN, and then you have to sum over all possible I and n. And that's the total momentum that the state carries. Now, this momentum is a momentum along the compact direction. So when we see it from the 3 plus 1 dimensional viewpoint, we will not see this as a momentum. What will it see it as? So Kaluza-Klein compactification we have done. So the momentum along the compact direction, you have seen the interpretation of momentum along compact direction. Okay, it's mass, but more importantly, it's also a charge, right? It's a charge. Why is it a charge? Because you see, the G we consider we use the fact that G99 is a scalar, right? What about G9 mu? What kind of a field will it appear from the 4-dimensional viewpoint? It's a vector field, right? And you know that the metric couples to the energy momentum plane, sir. So G9 mu is sourced by the momentum along the 9th direction, right? Because momentum is the source of energy momentum tensor is the source of gravity. Okay. So the 9 mu component will be sourced by the momentum along the 9th direction. So this quantity, the what we are calling momentum, sum over I equal to 1 to 8, sum over n over R9 RIN is the charge of G9 mu. Okay, so now we have constructed a quantum state which is charged under a gauge field, and that's besides the kind of quantum state we are looking for, right? The quantum state should be charged under a gauge field. So this is indeed charge, carries charge of G9 mu. Is it clear? But now you have to see whether the state is supersymmetric. Now, supersymmetric states, okay, or extremal black holes have this property that for a given charge, you have the minimal amount of mass. You cannot reduce the mass anymore. Let's look at this quantum state. Okay, energy is given by this expression over here. Charge is given by that expression over here. So for a given charge, if we want to minimize energy, you can see any restriction on the state, what kind of state you can have possibly. If for a given charge you want to minimize the energy. Pardon? See, the only difference between the charge and energy is that here you have just n over R9. Here you have mod n over R9. So imagine that you have two defined ends, one positive, one negative, right? For those the charge cancels out, but the energy adds, right? Energy is mod n over R9, right? So energy will add, charge will cancel out, right? So this means that we are reducing the charge but not the energy. Right? So those states are not extremal. Extremal states are those which have the minimum energy correspond to a given charge. Okay, so imagine that you have a positive n and negative n, they have cancelled out in the charge, right? Then we might have not included those, right? We have gotten lower energy state, right? Because the mod n over R9 contribution will not be there. So this shows that the extremal states are the ones which have all positive n or all negative n. All positive n or all negative n. What time does I start? 11:30. So yeah, I have some time, right? This counting is finished. Yes, for a given charge. Yeah, exactly. So that basically means that the state in extremal state carrying charge q or charge minus q have the same energy, right? But once you have fixed that the total charge is positive, then the constituents only should also all have positive charge, right? Because if you have some constituent having positive and some constituent having negative, then the charge cancels out, but the energy increases, right? So these are the supersymmetric states or extremal states. Okay, then everything should have positive n. What R9 I said is plays the role of the modulus, right? And we can see now why, right? So what is the minimal unit of charge here? Minimum unit of charge 1 by R9, right? So that was supposed to depend on the moduli, right? And indeed we see that large R9 corresponds to small unit of charge, right? That's where the counting we expect to be more reliable, right? Because implicitly in this setting up this problem this way, right? You have imagined that there is a long string, right, which is having small oscillations, right? If the string was very short, we couldn't have used this small oscillation approximation, right? Because a short string will fluctuate widely. So it's R9 going to large R9 limit that we can do this calculation is reliable, and that's exactly when Q naught is small, right? As we had discussed, that's the limit in which we expect the quantum calculations to be valid. Okay, so this also illustrates the role of the modulus, right? Large R9 is when you can do the calculation. So now let's just finish the counting. So suppose we are looking for a state states with charge n over R9. Okay, where n is some integer. Then by comparing with this, we see that n is just sum over I equal to 1 to 8 sum over n. Now n should be positive. N equal to 0 is a 0 mode. So n equal to 1 to infinity. Let me write it that way. Okay, n equal to 0 to infinity, you can write. So it doesn't really matter. N RIN. So the degenerate omega n. This is the number of ways we can choose integers RIN greater than or equal to 0 such that Is this clear? Right? For every choice of RIN, right, which satisfies this, we have a state of charge n. Right? Different RINs give different states. Right? So if you are counting how many states there are, okay, we just have to find how many ways you can choose these RINs so that this is satisfied. Oh, small RIN was this EIN dagger to the power RIN. How many times you have applied this oscillator on the vacuum? Right? Or in other words, occupancy number of the state IN of the harmonic of the IN state of the harmonic oscillator. Is this clear? So this counting you can easily do for small n. Okay, let's do it for n equal to 1. How many such RINs are there? 1. Anybody else? How many ways you can choose RIN so as to satisfy this? Remember, let me write this I equal to some I equal to 1 to 8, n equal to 0 to infinity, 8, right? Because each of these RIN are n has to be small n has to be 1 or 0, right? That is clear because you cannot apply RIN. Okay. So you can use the any of the 8 oscillators, right? Or you can choose RIN equal to 1 for either I equal to 1 or I equal to 2 or up to I equal to 8. Okay. So those are the all possible ways. So for n equal to 1, the number is 8. Okay. And you can do this way, right? But this becomes inconvenient very fast. Okay, that the combinatorially, right, it becomes a complicated problem. So an easier way to handle this is what is called the partition function, right? So I'll try to explain what the notion of partition function is. Okay. Eightfold degeneracy, exactly. Okay. And here everything is bosonic because we have only introduced bosonic oscillators so far, right? Later on, we'll deal with formulas. So the partition function f of q, okay, we introduce a variable q. Q is some complex variable. Is sum over n omega n q to the n. That's the definition. So if somebody gives me f of q, okay, I can just expand it in a Taylor series in q and read it out omega x. Right? So having f of q is useful, right? So we'll see how to write down the expression for f of q for this problem. So in this case, f of q will be given by omega n. We'll write down. So let me write sum over n q to the n, and for omega n, I'll write sum over each RIN. So let me write this. Then I'll okay. So let me explain this. So this product is over the sum. How many sums you have to do? There are basically infinite number of sums in one. Right? So this is saying that for every I and n, you sum over RIN from 1 to infinity. sorry, from 0 to infinity, right. So, this thing basically stands for sum over R11 equal to 0 to infinity, sum over R21 equal to 0 to infinity, up to sum over R81 equal to 0 to infinity, then R12 equal to 0 to infinity, and so on. Okay, so that this is what this thing means. Okay, because they are summing over all states, but there is a constraint because we have to satisfy this condition, right? And that condition is here, this Kronecker delta function. Okay, this is clear. So now what I am going to do is that I am going to do the sum over n first. I bring the q to the n here, and then do the sum over n using this Kronecker delta function. So I can write this again as product I equal to 1 to 8, product n equal to 1 to infinity, and then q to the power sum over I n n r I n. Is this clear what I have done? I just replaced n by this, Kronecker delta, right, and the sum over n is gone. The main advantage is that now there is a constraint, right. This constraint was making life difficult for us, right, because you have to count how many ways you can satisfy this, right, and satisfying this that you have to check, right. You choose your RIN and then you have to check. Now we don't have that constraint, so this is in fact easy to evaluate, right. So I write this. So this you can now rewrite. You can do this. Sorry, there is, I forgot the sum. The sum is still there. Only the sum over n has gone, right. This sum is still there. Sum over RIN equal to 0 to infinity. So this one basically now each RIN can be summed independently, okay, because there is a constraint. So we get product I equal to 1 to 8, product n equal to 1 to infinity. If this is confusing, it's just basically application of A plus B, C plus D as AC plus AD plus BC plus BD. Okay, just sum and product you have exchanged, right? This is basically if rewriting this you have to maybe put a little thought in saying this, but this rewriting is basically applying this formula, right, with multiple sums. But this now is easy to evaluate, right? This is just a geometric series 1 over 1 minus q to the n. So then this becomes product n equal to 1 to infinity 1 over 1 minus q to the n to the power 8. Okay, this is in fact a well-known function. Okay, it has modular properties, and that's what we can use to extract the degeneracy. but I'll leave it as an exercise. Okay, if you are inclined to using numerics. So take this function f of q, expand in power series in q, if you are used to using Mathematica, this can be done very easily. Okay, just put it in Mathematica and expand it. Calculate omega n. Okay, because the series expansion coefficients are the omega n's. And then fit with omega n for large n. Okay, and you can calculate A, B, C this way. Okay, that's by fitting the data. Okay, but this is of course not the most efficient way of extracting this, right? In there are theoretically there are analytical ways to extract these coefficients, right, which I may discuss later, okay, using some steepest descent. But if you are not familiar with these analytical methods, you can still extract this behavior of this function for large n just by expanding this out. This is a very simple function to expand, okay, and just read out these coefficients by fitting the data.
Yes, you want to send omega in terms of.
Well, because I know the answer, right? I mean, otherwise you have to fit with the A into the alpha and figure out what the alpha is also, right? I could have given to fit the alpha, right? In this case, I know the answer is goes as root n, right? That's why I wrote it like this. Okay? But as I said, you can extract, you can the fact that it goes as root n, including the coefficient, you can also derive analytically, right? By using some saddle point, because that which I'll discuss later. Okay, but all I'm saying here is that once you know f of q, extracting the behavior of this function for large n is not difficult, right? And large n is what you need, because black holes are made of lot of constituents, right? Because it has to have lot of charge. So this, as I said, is not a black hole, right? This doesn't make a black hole, okay? But the systems which make a black hole, their counting is done exactly in the same way, right? You have a lot of constituents, you express them as sum of harmonic oscillators, okay? And you count states of harmonic oscillators. Okay? So in fact, what I'll do is I'll write down for many of these systems, okay, some of these systems, the analog of f of q. And you will see that those analogs of f of q will always have structure like this, products. Each of these products come from one harmonic oscillator, right? This you can probably recognize, right? This 1 over 1 minus q to the n, right, came for a particular Ri n. For particular I and n, this sum gave 1 over 1 minus q to the n. So every harmonic oscillator will give an expansion of this kind, will give a factor of this kind, right? And we will see that the actual formulas which count black hole degeneracies are all of this kind, right? They have products of factors like this, right? Each of those factors coming from one harmonic oscillator. So next time I'll generalize this to different kinds of oscillators, so the kind of things that are relevant for black hole microcycle. Okay, but the physics is just this. I think my time is up.